Welcome to the deep dive. I'm really glad you're joining us today
Yeah, thanks for having me. This is going to be a fun one.
because we are looking at something today that fundamentally shifts how we build software with language models.
It really does. It changes the whole paradigm.
We're pulling our insights from a fascinating source text. It's titled Bridging Natural Language in Code via Function Calling.
Right.
And the mission for this deep dive for you listening is to get right under the hood. We want to uncover the actual mechanics of how an AI interacts with the real world.
Because it's not magic, even though it feels like it.
Exactly. I mean, we all know how fluid it feels on the front end,
Oh,
right?
totally. The user experience of modern AI is almost deceptively smooth.
Yeah.
As users, we just fire off these casual requests and get perfect answers back. But the reality of how these probabilistic models interface with deterministic software architectures,
It's a massive engineering hurdle.
it is a massive hurdle. It's incredibly difficult behind the scenes.
So let's frame this around a really practical scenario from the source text.
Okay, that's it.
Imagine you're building an application, right? And the user just types in, compare the weather in Tokyo and Berlin.
Sure. Simple request.
As a human reading that, yeah, it's simple. But the large language model itself, it doesn't have a weather app just running inside its weights.
Right. It doesn't actually know the weather.
No, it's
Right.
effectively locked in a box. So the core mystery for you listening is this. How does a text prediction engine know it needs to stop generating text, trigger an external weather API twice?
Once for Tokyo, once for Berlin.
Exactly.
Right.
Wait for the data and then synthesize a single natural response.
What's really fascinating here is the sheer orchestration involved in that.
Yeah, how does it do it?
Well, a language model natively has absolutely no concept of an API or a database.
It's just guessing the next word.
Exactly. It just predicts the next token.
Yeah.
So to bridge that gap between a conversational request and an actual functional API call, developers really had to evolve their approach over time.
And the source text walks through three distinct phases of this evolution, doesn't it?
It does, yeah. Showing how we finally managed to force these chatty, unpredictable models into the rigid, unforgiving constraints of standard software development.
Right. And it wasn't a straight path.
Not at all.
If we look at the first method the text covers, it's plain text completion.
Oh boy. Plain text.
The absolute wild west of API interactions.
That is the perfect way to describe it.
You throw a prompt at the model and it throws back a wall of unstructured text.
Which, is perfectly fine if you're just building a chatbot meant to hold a conversation with a human.
Sure.
But if we connect that to the bigger picture of back-end engineering, unstructured text is a total nightmare.
Why is it so bad?
Because software relies on predictability.
Mm-hmm.
When you write code that expects a certain input to trigger a certain function, you just can't rely on a system that might change its phrasing every single time it runs.
Okay, let's unpack this for the listener. Let's say you're building a simple sorting application. You pass an input to the LLM, and you just need it to output yes or no.
Just a binary choice.
Right. If your code gets a yes, it routes the data to database A. If no, database B.
Simple enough.
But these models, especially the ones that are fine-tuned to be really helpful and polite,
The RLHF models.
yeah, they are heavily biased toward being conversational. So instead of just outputting the token for yes, the model outputs sure. Based on the parameters you provided, I can confidently say that the answer is yes.
And right there, your parsing logic just shatters.
It breaks completely.
Standard software uses things like regex, regular expressions, to find patterns in text.
Right.
But regex is incredibly brittle when it's faced with infinite conversational variations. I actually remember a project a few years ago.
Oh, yeah.
Yeah, where a team tried to build a sentiment analyzer using plain text completion. They had these massive regex blocks trying to catch every possible way the model might say positive or negative.
That sounds exhausting.
It worked in testing. But the second it went to production, the model started saying things like, the overall tone leans toward a positive sentiment.
And the regex didn't catch it.
Missed it entirely. The entire routing system went down.
Wow. I can entirely picture that server crashing.
Oh, it did.
But wait, if that's the case, why wouldn't developers just write a hyper-specific prompt?
Like what?
Like, only output the word yes or no. Do not add any conversational filler. Your life depends on it.
Right, the all caps threatening prompt.
Yeah. Why doesn't that solve it?
Well, this raises a really important question about the nature of prompting itself. Prompting is fundamentally just a request.
A request, not a command.
Exactly. You are heavily weighting the probability that the model will follow your instructions, but you aren't changing its underlying architecture.
It's still a probabilistic engine.
Right. You might get yes 99 times, but on the 100th run, some weird combination of input tokens shifts the probability distribution.
And it starts talking again.
Yeah, it starts apologizing for not having enough context before it finally gives you the answer. And in software engineering, a 1% failure rate on a core routing function is catastrophic.
It's unusable, so developers realized they needed a way to force the model into a rigid box.
They absolutely had to.
And I know JSON mode was the massive buzzword a while back to supposedly solve this exact issue.
It was huge.
The source text brings this up as the second major evolutionary step.
And it was definitely a necessary evolution.
Hmm.
JSON mode essentially applies a structural constraint to the model's output.
So it forces a format.
Yes. When you toggle JSON mode on in the API, you are guaranteeing that the model's output will be valid, parsable JSON.
Okay.
The curly braces will match, the syntax will be perfectly correct, and it won't just be a floating paragraph of text.
Now, on the surface, that sounds like a total fix.
It does.
You go from having to write brittle regex for a messy paragraph to receiving a neatly organized data object.
Right, you can just tell your application to look for the keys and values.
So what's the catch?
Well, it feels safer, certainly. But does a valid JSON structure actually guarantee valid data content?
Ah.
The source text is very clear on this. JSON mode only guarantees the syntax. It offers zero guarantees about the specific keys, fields, or values the model decides to generate inside that JSON object.
Oh, I see. And the source text has a really great example of this fatal flaw.
Let's hear it.
So let's say your code is specifically looking for a data key labeled category.
Right, spelled out CATEGORY.
Exactly. Your downstream application is hard-coded to extract the value associated with that exact word to know what to do next.
Okay.
But the LLM, in its probabilistic nature, decides to optimize the output and returns the key as just cat instead.
And that's where the system breaks again.
Because it's looking for category.
Exactly. The JSON is perfectly valid. The parser reads it without throwing a syntax error.
The braces match.
Right. But when your application queries the object for the category key, it returns a null value.
Because the model named it cat.
Yes. The software is blind to the semantic meaning. It doesn't know that cat means category.
It's just matching strings.
Exactly.
But couldn't a developer just write a fallback script?
What do you mean?
Like, if the key is cat or cadeg or classification, just map it back to category in the code. Why is JSON mode still considered a false comfort if you can just handle those exceptions?
Because of scaling. What you're describing is a game of whack-a-mole.
Okay, fair.
Sure, you can write a fallback script for cat. But what if the model outputs category name tomorrow?
Oh, I see.
Or what if you're passing a complex data object with 50 different fields? You cannot write defensive code against the infinite probabilistic variations of a language model.
It's just too unpredictable.
It is technically impossible to map every hallucinated key name. JSON mode gives developers the illusion of control, but the data schema itself is still entirely at the mercy of the model's next token prediction.
The false comfort of an organized disaster.
That is a great way to put it.
That makes total sense. But here is where it gets really interesting.
Yeah.
The source text introduces the third method, declaring it the ultimate solution for this problem, function calling.
The holy grail.
If we look at why function calling is the standard today, it comes down to deterministic control over a probabilistic system.
Exactly. Function calling removes the guesswork completely.
How so?
It allows developers to pass a strict schema, a literal blueprint to the API, dictating the exact structure of the response.
Okay, let's use the email classification example from the text to really visualize this for you listening.
Good example.
If you're building an automated inbox manager, you don't just ask the model to categorize the email and hope it gives you a good label.
No, you can't rely on hope.
With function calling, you define an enum.
A pre-approved, exhaustive list of acceptable categories.
Exactly. You tell the API the category field must be either urgent, newsletter, or spam. Those are the only three options.
But because of that, the model cannot invent a new category called promotions.
Right.
It cannot shorten urgent to erg. It is locked in.
And it goes beyond just text strings, right?
Way beyond.
The source notes, you can enforce data types.
Yes.
So if you want a confidence score for that categorization, you can dictate that the field must be a float, a numerical value.
Right.
The model can't spell out the words 95%. It has to return the actual digits, like 0.95.
And you can even specify which fields are absolutely required and which are optional.
Like adding an optional field for a summary of the email?
Exactly. The crucial distinction here between this and JSON mode is the API level guarantee.
It's enforced.
Yes. You are not writing a system prompt begging the model to use your specific keys. You are passing a programmatic schema, and the API enforces that schema.
So you know what you're getting.
When you receive the payload back, you know with 100% certainty that the category key exists, that it's spelled correctly, and that the value is one of your predefined enums.
And your downstream code can run flawlessly.
Without any brittle fallback scripts.
But here is the massive contradiction that the source text brings up, and I found this fascinating.
Yeah.
Even when we get this flawlessly structured, strict payload back from the API,
Right.
the underlying language model hasn't changed.
It hasn't.
It is still an autoregressive engine. It is still just probabilistically guessing the next token.
Right. The architecture of the neural network hasn't suddenly become a rigid database.
Exactly.
It's still a massive web of weights and biases generating text piece by piece.
So how does that work?
It's brilliant, honestly.
How do you take a machine designed to probabilistically hallucinate human-sounding text and force it to output perfect, strict data schemas without fail?
This is the real technical secret behind function calling.
Okay.
And it's what the source refers to as constrained decoding or guided generation.
Constrained decoding.
And understand this, we have to look at what happens at the very split second before the model outputs a token.
The guardian at the gate.
Yes.
The source uses this analogy of filling out a digital form with impossible to bypass validation, which is a great way to visualize it.
It is.
But what is actually happening at the compute level?
Okay, so if we dive into the mechanics, every time an LLM is about to generate a token, it creates a probability distribution across its entire vocabulary.
Okay, so it looks at all the words it knows.
Right. Let's say the vocabulary is 100,000 different tokens.
Oh.
The model assigns a percentage to every single one of them based on the context.
Got it.
Normally, it just samples from the top probabilities and outputs that token.
Right. So if the prompt is the sky is,
The token for blue has a massive probability.
and the token for zebra has a near zero probability.
Exactly. But with constrained decoding, we introduce a finite state machine.
A strict set of rules.
Right. A set of rules that sits right between that probability distribution and the actual output. This is your guardian.
Okay, so how does the guardian intervene?
It looks at the schema you provided in your function call. Let's say your schema demands a Boolean value right now, true or false.
Okay.
The model generates its 100,000 probabilities. The guardian looks at them, and it instantly masks or applies a negative infinity logit bias to 99,998 of those tokens.
Wow.
Yeah.
So it literally zeroes out the probability of any token that isn't true or false.
Precisely. It mathematically zeroes them out.
That's incredible.
Even if the model's conversational training makes it really, really want to output the token, for sure, because it has a 90% probability.
The guardian steps in.
The guardian zeroes that probability before the sampling even happens.
He doesn't even get the chance.
No. The model is physically incapable of outputting anything other than the tokens that fit the schema at that exact moment in the generation sequence.
That is an incredibly elegant solution.
It really is.
It's not a post-generation filter that rejects a bad answer and asks the model to try again.
Exactly. That would be too slow.
It's manipulating the probabilistic sampling in real time. It forces compliance at the token level.
And what's brilliant about it is that it requires no fine-tuning or retraining of the underlying model.
You don't have to touch the weights.
Right. You are just applying an inference-level mask. If the schema requires a bracket, the only token allowed through is a bracket.
And if it requires a digit between 0 and 9.
All alphabet tokens are masked.
Yeah.
That is how you get a 100% reliable data structure out of a system that is inherently unpredictable.
So what does this all mean for the broader landscape of AI?
It's foundational.
We've traced this evolution from the chaotic rejects nightmares of plain text, past the false comfort of JSON mode, down to manipulating probability distributions with constrained decoding.
Yeah.
Why is this specific technical achievement so critical for the future?
It's critical because this guaranteed structure is the fundamental building block for AI agents.
Agents, right.
An LLM on its own is just a brain in a jar.
It just sits there.
It can reason, it can synthesize text, but it can't actually do anything.
Right.
To take action, it has to communicate with other software. Databases, APIs, payment gateways, smart home devices.
And all of those external systems require strict deterministic inputs.
Exactly. Which brings us right back to our first scenario.
The user asking for the weather in Tokyo and Berlin.
Right. With function calling, the LLM parses the user's natural language request. It realizes it needs data.
It needs to check the outside ones.
Yes. It looks at the tools you've given it, say a weather API. The model begins to generate the request to that API.
Okay.
And because of constrained decoding, the Guardian ensures that the model outputs a perfectly formatted JSON payload with the exact keys the weather API requires.
Location, unit of measurement, date.
Exactly. It flawlessly generates the Tokyo request, receives the data, flawlessly generates the Berlin request, receives the data.
And then puts it all together.
Yes.
Yeah.
It seamlessly translates all of that structured data back into a natural language response for the user.
It's the bridge.
It really is.
You have the fluid, nuanced, highly unpredictable world of human language on one side.
And the rigid, typed, structured world of computer code on the other.
And function calling is the translation layer that allows them to interact without everything crashing.
If we connect this to the bigger picture, it's what separates a chatbot from an autonomous system.
That makes total sense.
Without constrained decoding, you couldn't trust an AI to trigger a database update or book a flight, because the risk of a hallucinated data key would be just too high.
It could book the wrong flight or corrupt the database.
Exactly. By forcing token-level compliance, developers can actually trust the model's output in mission-critical software pipelines.
That completely reframes how I think about these applications.
How so?
It's not that the AI has learned to code perfectly. It's that the inference engine is strictly guiding its probabilistic nature to ensure it doesn't break the rules.
It's a massive leap forward in making AI reliable. But exploring how this guardian mechanism works, masking probabilities at the token level to force compliance, it raises an incredibly important and maybe slightly unsettling question to think about.
Oh, I have a feeling I know where this is going.
We just spent this entire deep dive looking at how constrained decoding acts as an uncompromising guardian,
Right.
physically preventing an AI from generating invalid data tokens to ensure a software program runs reliably.
It mathematically zeroes out the bad token.
Exactly. It literally masks the vocabulary.
Yeah.
But if developers have the architecture to control an AI at the token level, surgically restricting the output of specific data formats,
Yeah.
could this exact same inference-level guardian eventually be used to physically restrict the ideas, concepts, or opinions an AI is allowed to express in natural human conversation?
Wow. That is a wild thought to end on.
It's something to think about.
If you can zero out the probability of a syntax error, you could theoretically zero out the probability of a restricted concept before the model even formulates the thought. That's a whole different kind of bridge. Well, thank you so much for exploring this with me today.
It was a pleasure. Thanks for having me.
And thank you all for joining us on this deep dive. Keep questioning the systems running behind the screens, and we will catch you next time.